The idea of today's talk is, first of all, to motivate the need and the importance of model-based testing when we deal with web applications, and in particular with web 2.0 applications. I will tell you also what I mean by this. And after convincing you about this motivation, I will proceed with the 3 key problems that you have when you try to do model-based testing in general and for web applications in particular. So first problem is getting the model. Second problem, using properly it for testing. And finally, defining the oracle that is a key component in testing. So let's start with web applications and web 2.0. So first of all, what is web 2.0? Actually, it's a fuzzy notion. Nobody knows. If you ask different people, you get different definitions. So I will take a quite narrow and, let's say, specific view on this, which is the following. To me, and for, let's say, in the scope of this talk, a Web 2.0 application is one where most of the computation is delegated to the client side. So in traditional web application, there is a continuous interaction between a web page and the web server. So the web page provides links and forms, then there is a request, a synchronous request that goes to the server, to the web server, because there's a link pressed or a form submitted, and then the client is frozen. It waits for the next page. The next page comes, and then you continue with the interaction. So it's submission, wait, and then next page. That's the classic paradigm. With Web 2.0, the new paradigm allow developers to build applications where the client is always active and responsive. And most of the requests are asynchronous. So to me, this is the key keyword, the most important keyword that characterizes Web 2.0. So this is implemented in different ways depending on the technologies. If you are using Ajax, there is this HTTP request object that can be used to pass an asynchronous request to the web server, and then when the response comes, the handler function for the onReady state change event is activated. So you define a handler for the onReady state change. When this event occurs on the HTTP request object, then the handler is activated and you can do whatever you want. Take this example. So this is a single page application that manages cell phones buying. So there's no traditional interaction where the client is frozen. Everything happens in a single page. If you want to make some operations that add a couple of new cell phones on the page, then an HTTP request for this operation is sent to the server, and when this handler function is activated, the DOM tree for this page, for this single page, is manipulated, and for instance, the 2 images of these 2 additional cell phones are added dynamically to the web page. So this is the context where we want to do testing, and the point is that in this context, it's very difficult to base testing on the source code because there is a lot of dynamicity. The code is split between client and server. Fragments of code can be sent back from the server to the client dynamically and can be integrated into the DOM. So there is no such fixed notion of source code as in more traditional applications. Requirements are also never defined in such a way that you can use them as a basis for testing, and models, on the other hand, represent a very interesting alternative. So let's take a shopping cart, a very simple web application. Here we can define all the relevant behaviors of this application through a very simple model. We have an initial state, then we enter into a state where the cart is empty, so the total is 0 and the number of items in the cart is 0, and then by add or remove or empty events, we can move to the other state where there's something in the cart. That's very simple, but you can see from this very simple example that all the important behaviors of a cart application are captured very well in a model. If you are able to exercise the model, so to derive test cases that exercise the model thoroughly, then you have tested all the relevant behaviors. So the intuition behind model-based testing of web applications is that we have a model that captures all the relevant functionalities and behaviors that we want to test in the application under test. So this is the context of application of model-based testing to the web. The next problems are, first, how to get the model, second, how to use it, and third, how to define an oracle for the test cases. So first problem, getting the model, there's at least 3 possibilities. The first one is the obvious. You can manually define it, asking developers to spend some of their time to do it. That's a possibility. It's done in practice several times. But we explored a couple of alternatives which are based on inference of the model from observations. And the first possibility is event-based inference. The second is state-based inference. So let's start with event-based inference of a model. Here, the starting point is a collection of logs that capture sequences of events that have been observed in real executions of the application. So these are real behaviors of the application under test. So if we have these, then the problem of inferring a finite state model of the application is basically a grammar learning problem, because a finite state model of the application is a regular, one of the alternative ways in which you can express a regular language. So you can use regular expressions, or you can use finite state machines. So there's a number of grammar learning algorithms that can be applied to obtain this representation, starting from some information like this one. K-tail has been used quite extensively. The problem with this algorithm, if we apply them to the inference of a model that is useful for web testing, is that you have 2 conflicting objectives. One is the amount of approximation, and if the model is over-approximating the actual system, then we will have a lot of behaviors in the model that can never happen in reality. So one goal when we infer those models is to minimize over-approximation. At the same time, we don't want to under-approximate the real behaviors. We don't want to express in the model just the behaviors that we observed. We want to express all possible behaviors. So clearly, these are contrasting goals. And for them, we can define metrics that we can try to optimize using, for instance, search-based algorithms. And I will show you that it's possible to optimize these metrics using a multi-objective approach by means of search-based algorithms. In particular, we introduce an OBS, which is a metric that introduces an approximate quantification of the first goal. So an OBS measures the number of event sequences that are legal, that are acceptable for the model, that were never observed in any real execution of the system. Second metric is unrec. It's the number of real, so of observed event sequences that are not recognized, that are not accepted by the model. So if we keep only these 2 metrics, there's a trivial way to optimize them and make them 0. And it is to take all the traces that are available and to put them in parallel as a non-deterministic choice among them. If you do that, then there's no unobserved behavior, because all the traces, all and only the traces are in the model, and unrec is also 0 because every trace is recognized. What's the problem of this solution? Of course, the problem is that the size of the model explodes. Whenever you add one more trace, you add it completely to the model. So the size of the model becomes the number of events in all the traces that you ever observe. So if you don't introduce these, optimizing these 2 in isolation is not enough. We want small models, so small models of manageable size that have low number of unobserved event sequences and a small number of unrecognized traces. So as I mentioned before, we did this through a multi-objective optimization approach. in which we assume that we are able to generate a set of candidate solutions, a set of candidate models. For these, we can evaluate these three metrics that characterize, let's say, the quality of the inferred model. We select the non-dominated model, so a model dominates another one if it is better on at least one dimension, one of these three dimensions, and it is no worse in all the others. We don't want to consider dominated models, so we take only the non-dominated models, which are represented in the so-called Pareto front, and then we apply some operations that transform the models and produce new candidate models. Then we cycle, and after a number of iterations, we get a set of models that minimize these three metrics in the Pareto front. Here you can see how we manipulate the models to get better models. It's possible to take two existing models and try to combine them by union or intersection. So the idea of union is that we can accept more behaviors in the union, so we reduce the unrec matrix by means of union. Union is typically produces a non-deterministic model, but there's a power set construction algorithm which is very well known that can transform a non-deterministic finite state machine into a deterministic one. The idea of intersection is that we reduce the unobs. We reduce the possibility of having illegal behaviors in the model. So we take only behaviors that are admitted by two or more models. The other two operations that we use to do manipulation of the models are add trace and merge state. So add trace is a way to clearly reduce the number of unrecognized traces. The trace that we want to recognize is added in parallel as a non-deterministic choice. By power set construction, we can make this model deterministic. The merge state corresponds to what k-tail does. When there are two states in the model that are followed by the same sequences of events up to a length k, then the two states are merged. So with these operators, we can optimize the key metrics that characterize the quality of the matrix of the models, and we can get an event-based model inferred from the execution traces. So to summarize, in event-based inference, the idea is that we apply regular language learning to obtain models, but we also minimize three metrics that characterize the level of over and under approximation of the model. If you want to see more about the details of the algorithms and the experimental results that we obtained, I point you to an ICST paper that we published in 2012. The other option is a state-based inference. That's quite a difference, and also it requires different logging information. So in the logs, instead of assuming that we have just the events in the sequence, we assume that we have also the information about the concrete state. This can be a projection of the state, because typically the state is huge, but still it's concrete. So we have concrete values for every state variable that we consider. Then we apply an abstraction function to the concrete state, and we get a state-based model. So if we take these two as abstraction functions, so we distinguish only total 0, number of Li 0, or total greater than 0, number of Li greater than 0, from these traces, you get this model of the application. So the key difficult step in this approach is the definition of the abstraction functions. Here you can see some examples that can be defined for web applications, but in general, it's important to have a custom ad hoc abstraction function to obtain good models. So this step can be quite expensive for the developers. So we try to investigate the possibility of automating also this step. And the idea is that abstraction functions can be generated automatically by first taking the concrete states and applying clustering to them. So we group together states, concrete states that have similarities. Second, we apply invariant inference, in particular data invariant inference, to characterize the clusters. So inside each cluster, we try to automatically infer the invariants that hold for the concrete states that are in such cluster. For instance, for this cluster, you get total 0, number of like 0. And here you can see some other functions that characterize the concrete states in each cluster. If you can do this chain, then you get the candidate abstraction functions. The problem is, how do we get optimal abstraction functions? So the problem can be formulated as a partitioning problem. So if we can partition the concrete states optimally, then we would get optimal abstraction functions that eventually produce an optimal state-based model of the application. What is the notion of optimality that we want to enforce here? It's very similar to the previous one. We want, in the end, to get a good model of the application. So a good model is a model where the size is reduced. We don't want a huge model where every concrete state is represented explicitly. We want to reduce the non-deterministic transitions in the model. Here you have to notice that the non-determinism cannot be resolved by power set construction because states are meaningful. We cannot just introduce new states or remove states arbitrarily as in event-based modeling. So here, non-determinism of the model is a problem, and we want to minimize it. And infeasibility corresponds to the unobs metrics that I introduced earlier. So we don't want the model to include a lot of behaviors that are not possible in the real system. So if we introduce these free optimality metrics, we can choose a multi-objective optimization approach, which is similar to the previous one. The key difference is the representation of the problem. In the previous multi-objective optimization, here we try to directly manipulate the models. In this setting, we manipulate partitions of the concrete states that are then associated with abstraction functions that produce the models. So a partition is an assignment of concrete states to clusters. So it's basically a vector of integers. This partition here is a vector of 8 integers telling that the first concrete state belongs to cluster number 1, the second to cluster number 2, and so on. So you can obtain different clustering, different partitioning of the concrete states by defining these different integer vectors. For each partition, we apply invariant inference to obtain the model, and we measure these free quality indicators directly on the model. So each of these candidate partitions produces a triplet of quality metrics. Then we select the non-dominated partitions, which are part of the Pareto front, and we apply genetic operators to produce new candidate partitions that will generate new abstraction functions automatically. In this case, the genetic operators that we use are very simple because the representation is also very simple. Here, you can introduce mutation that just changes a single assignment of a concrete state to a cluster and reassigns it to another cluster, or we can introduce crossover that takes two vectors of integers. This operator cuts the two vectors in the middle and swaps the tails of the two representation of the partitioning. So in this way, we get a set of optimal partitions that are associated to abstraction functions such that if you compute the models using these abstraction functions, the metrics for these models are non-dominated metrics. So in this example, we have 6 partitions, 6 abstraction functions inferred from the concrete states, and 6 models. So the first 4 are non-dominated models. Here, if you look at the metrics, there's no dominance relations, while if you pick, for instance, A5, A5 is worse than A1 in terms of size. It's worse in terms of non-deterministic transitions, and it's the same in terms of infeasibility. So clearly, A1 is dominating A5, and we just discard A5 from the solution set. So to conclude on this part, it's possible to define manually the abstraction functions that are used for state-based inference, but it's also an option to infer these abstraction functions automatically by means of clustering and multi-objective optimization. Of course, in this seminar, I just give you a quick overview of the algorithms that we implemented. I don't mention any empirical results. If you are interested, you can have a look at the papers where this is described in more detail. OK, so either manually defined or inferred, let's assume we have a model. The problem is that things change, and Web 2.0 applications change very quickly. So the next question is, well, what do we do when the web application evolves? Do we have to redefine the model completely, or is there a way to evolve smoothly the model to the new version of the application? So as usual, manual evolution is an option. It's the most expensive one. Inference from scratch is another option, but it can be quite expensive because it involves, well, a lot of computation, and also in the end you get a Pareto front with multiple alternative models that have to be chosen manually. So the ideal solution when the application evolves is to be able to automatically and incrementally update the model. So can we do that, and what are the problems? Well, so if we have a state-based models like this one, when a new state or a new transition comes in, so when a new transition like credit appears in the logs that was never observed before, and then now we can just add the new transition and the new state, provided the abstraction functions that we have are able to handle the new state. So if this is possible, then we can quite easily do this incremental update of the model. If the abstraction functions are not adequate for the new state, then we have to introduce new abstraction functions, and then the problem is to do it manually or to try to infer them automatically. New transitions to existing states are also very easy to handle. They are just added to the model. The difficult part is the removal of things that become obsolete in a new application. Because the only way to decide that something is really obsolete is by observing that a given event or a given state did not appear in any execution for a long time. And the question is, how long must be a time to be long enough to allow us for the deletion of an element of a transition or of a state from the model? So we developed an estimation of the expiration time, which is based on some analysis of the maximum delta between transitions in the event log. And then the idea is that we can schedule a deletion time for transitions based on the current time and on this estimated expiration time. When a given transition is not observed up to the scheduled deletion time, for instance, here you can see an example where the two transitions, RAM1 and RAM2, have a deletion time of 60 and the current time is now 60, then we can remove these two transitions from the model. But clearly, as you can imagine, that's quite difficult, and it's exposed to false alarms. You can remove something that reappears later, or you could miss a removal for a long time while the element has become obsolete quite early in the past. If we can remove transitions that become obsolete, then it's quite easy to remove also states that become unreachable because of the removal of transitions. So to summarize, it is possible to automatically and incrementally evolve models. The problem is removal of elements that are obsolete, because if the only input is observations of the real executions, it's quite difficult to make decisions on the point in time when a given model element has become old enough. If you want to see the algorithm that we actually implemented for the estimation, then I point you to this paper. OK, so we have seen that it's possible to get the model by inference or by other means, and it's possible to evolve it. The next question is how do we use it for testing? And in particular, I will focus on how to generate test sequences from the model, how to generate test data from the model, and how to ensure that the test cases that we get are actually feasible. So for test sequence generation, it's possible to adopt classical approaches that are based on the traversal of the model. So they are based on graph visit algorithms that make sure that some coverage criterion is met, like transition coverage. If we apply random visit algorithms, then we start from the initial state, we randomly visit the graph, we get event sequences. Some might be redundant because they cover transitions that were already covered before, so we can remove them. And eventually we get a test suite, an abstract test suite because it's defined on the model, that covers all the transitions. Alternative ways to achieve this is by means of depth first or breadth first visits of the model. Another possible approach to generate event sequences from the model is based on the notion of semantic interactions. So we have a semantic interaction between two events if they don't commute in terms of the states that are reached when applying these sequences on the model. Let's consider the previous model with the addition of this transition with events, text, and subject. Here we have four semantically interacting event pairs. So text and submit interact semantically because we reach different states if we apply the sequence text submit or submit text. In particular, if we start from S11, if we apply text submit, we end up with S17. If we apply submit text, we end up with S11. So two different states. The intuition behind semantic interactions of events is that if two events interact semantically, there must be some dependencies between what is done by the first event and what is done by the second, because if we swap the two events, we get to a different application state. So if events interact semantically, then probably they are the most important to test. And it's possible to define an adequacy criterion which is based on the coverage of pairs of events that interact semantically. So if we apply this criterion to this model, then we get these test cases that achieve the coverage of all pairs of events that interact semantically. Another criterion that can be used for the generation of event sequences is test suite diversity. Sorry, but I want to try to take off my coat. So diversity can be an important component of a test suite. If we have diverse test cases that exercise different functionalities differently, then it's more likely that they expose faults. And it's possible to introduce different diversity metrics. For instance, metrics can be based on the execution frequency. So if we collect the execution frequency of event sequences, then we can measure the minimum or the average difference. Here we take the Euclidean distance between frequency vectors to characterize the diversity of a test suite. So if we do this, then when we have several candidate suites, we can optimize these metrics. A matrix of the average or minimum distance that characterize the frequency of execution of events of different suites. Then we can apply operators that manipulate the test suites by adding or replacing existing test sequences until we get a suite that maximizes the internal diversity. So to summarize, it's possible to generate abstract test sequences that can be used for testing according to different criteria. Some criteria can be based just on graph visit, others on semantic interactions between events, and other criteria can be based on diversity. We have implemented all these criteria, and we have also evaluated them empirically, and you can find the implementation and the evaluation in a couple of papers that we published. OK, so we have abstract test cases. So test cases defined on the model. The problem is that to make them concretely executable against the application, we also need input data. So if we take this example, the various events will have parameters that we have to provide in order to make sure that the execution follows the event sequence that we want to test. How can we obtain input data for the parameters? One possible way to do this is by taking the model, which can be manually specified or which can be obtained through inference, and we can automatically generate a monitor that represents the various execution paths that are possible in the model. And by properly transforming the model into a monitor, which is a piece of code, we can ensure that this theorem holds. So transition coverage on the model can be achieved if and only if all non-error branch coverage is achieved on the monitor. So to be more concrete, it's possible to transform a given model into a piece of code where the various transitions are modeled explicitly as a sequence of switch case statements that determine what's the next state. In turn, this is determined by the actual behavior of the system under test. So we assume that we can run the system under test for a given event, and we can observe some of the internal state of the application. Based on the resulting state, we can decide what's the next state. And if we can do this by covering all these branches, which are the non-error branches, so we don't consider, for instance, the case where the model is under-specified, we are sure that we have produced enough input data to cover all the transitions of the original model. So here, for instance, we will get enough integer values when RAM is called to make sure that all these three branches are explored. So the problem now has become how to cover all the branches that we have in a piece of code. This is Java code. And for this, there's a number of existing approaches that can be used. In particular, we applied the tool EvoSuite, which is based on a search-based test case generation approach. And the test cases that are produced by EvoSuite, here you can see a sample, are test cases that cover all the branches of the monitor. So they provide integer values to the parameters that are needed by the event so as to achieve full branch coverage. At the same time, because of the theorem that I showed you before, by running these test cases, we also achieve transition coverage of the initial model. So that's one possible strategy for input data generation. The other possibility is based on combinatorial testing. So if we take an input sequence and we consider the parameters that we have to provide to make this sequence executable, it's possible to define a partitioning of the input space into equivalence classes. So for instance, for event subject, we have one parameter, and we might have three equivalence classes for this string parameter that we have to provide. The empty string, an alphanumeric string for which we have a sample that looks like this, or a string including special characters for which we can have a sample that looks like this. And for the parameter of the text event, we can have, again, three equivalence classes and three or more samples of representative elements of these classes. If we do this decomposition into equivalence classes for the input data, then we can target some coverage criteria on these classes, like the pairwise combination coverage. In this example, pairwise combination accounts for producing these 9 test cases that cover all the 9 possible combinations, pairwise combinations of elements that we have for these 2 parameters. So clearly for a single test case, these can produce a lot of combinations, but since we are interested in covering all pairwise combinations across all the event sequences that we generate from the model, we can have some redundancy elimination. So if one pairwise combination is covered by one event sequence, we don't need to cover it in another event sequence, so as to minimize the number of test cases that we eventually have to run against the application. So to summarize on the test data generation part, we have developed a method which is based on branch coverage on a monitor, which is a piece of code which is generated automatically from the model. The second possibility is based on combinatorial pairwise input coverage. And again, I point you to some paper where you can find more details on this topic. The last important question when we try to make these sequences actually executable against the application is infeasibility. In fact, these models are actually an abstraction of the semantics. So a lot of dependencies and constraints that hold for the real application are not represented explicitly in these models. And the test cases that we produce, the abstract test cases that we generate in the model, might violate these missing dependencies and constraints. If a sequence is infeasible because of these violations, then it will not be possible in any way, either through EvoSuite or through combinatorial testing or whatsoever. It will be impossible to make it an executable test case, which means this event sequence will never be run against the application, which also means that the coverage that we achieve on the model is diminished, because this sequence is not really executed. And the coverage and the fault detection that we achieve against the real application is also diminished. So feasibility is a big problem when we do model-based testing. It is addressed typically manually, so the developer has to recognize that it's not possible to really produce a concrete execution, a concrete test case for an abstract test sequence, and this is very expensive and very difficult. And also remedying to these infeasible sequences is difficult because the missing coverage on the model must be repaired by some other test sequence that must be defined manually by the developers. So infeasibility can cause a lot of trouble in the actual execution of tests against the application. It can reduce coverage and fault detection substantially, and it can involve substantial manual effort. So, and in the general case, it's undecidable. So knowing if, given an abstract test case, it's possible to produce a concrete one that will be executable is undecidable in the general case. So if we take this example, this is a web application that manages nodes. From the initial state, you can access existing nodes if you go this way and edit them and submit the edits. So edit, then change the text, change the subject, and then submit the new version. Or you can insert a new node. An implicit constraint that might be not represented in the model can be that if you choose this, if you insert a new node in the application, then it's mandatory to insert a non-empty text and a non-empty subject. So let's assume that we have this constraint that is implicit in the model, but is explicit in the application under test. Then, if we take some of the test cases generated by random visit, DFV, or BFV, we can see that some are OK. Here we do new node, then text, subject, and submit, so it's feasible. But some are not OK. Some are not actually executable against the system. Here, for instance, we create a new node, and we immediately submit it, which is not allowed. So how can we predict feasibility to make sure that we maximize the number of feasible sequences that we get from the model? So the intuition here is that in natural language processing, n-grams have proved to be very useful for word prediction, and word prediction in turn is very useful to do tasks like machine translation and speech recognition. So in model-based testing, what we propose is to use n-grams to try to predict the next feasible event. So based on the observation of n-tuples in real executions, we estimate the probability of the next event given the previous n-1 events. So let's take this example, and let's assume that we have computed the 2 grams for this application. So if the sequence new node submit is illegal in the real application, we will never observe the bgram new node submit in any execution. So the estimated condition probability of submit given new node as preceding event will be 0. While here you get 0.8 and 0.2 for the probability of subject or text given new node. So clearly, if we use these probabilities to generate a test sequence, we will never commit the error of producing new node submit, because we have a 0 probability of producing a submit after new node. Then, if, for instance, we follow new node and then we choose to emit submit, so to generate the event subject, we look at the other bgrams, so the condition probability where the context is provided by subject, by this event. And here there is still some probability of choosing submit, which is, again, illegal. So with bgrams, we have reduced the probability of generating infeasible event sequences, but it's not completely eliminated. If here we choose, after choosing a subject, if here we choose submit, which has low probability but not 0 probability, then we end up with an infeasible sequence. So clearly, if we were to avoid also this case, what we would need is a longer context. If we use 3 grams instead of bgrams, then the probability of submit given subject, comma, new node will be 0. So as you can see, using longer contexts is beneficial for the feasibility of the sequences. The problem is that the longer is the context that we use, the larger is the corpus that is needed to estimate condition probabilities. In particular, the size of the corpus for the estimation grows exponentially with the size of the context. So this means that in practice, if you choose a very big n, you will have very few evidences of the possible n-tuples. So you will have very few condition probabilities for which the estimate is different from 0. So our idea is that, well, if we have long n-tuples for the current estimation, we use them, and we give them a high weight. If we don't have any long n-tuple, we use whatever shorter n-tuples we have, and we give them a lower and lower weight. So the condition probabilities that we use are actually interpolated across contexts where the size of the context is between 1 and n minus 1. When the context that we use, so when the context for which we have a non-zero probability is high, the weight that we use for this probability is exponentially high, 2 to the k. But if this probability for a high k is 0, still we can use probabilities with lower k's and with lower weight. Here alpha is just a normalization factor to get probabilities that satisfy the normal probability rule. So you can see in the paper, if you are interested, how alpha is computed, but it's a trivial normalization factor. So let's take an example. Here, let's assume we have these traces and this model. If we apply n-gram 2, and we have these 2 sequences for which we have to compute the next event, so for the bgrams, we look only at the preceding event, which is C. When the preceding event is C, the probability of E is 6 over 15, so it's 0.4. It is 9 over 16, so 0.6 for D. If we use trigrams, then for the first sequence, it's OK. We can do an estimation because the sequence BC is present here and here. And we get 0.1, 0.9. But for the second sequence, YC is actually in no execution log. So we have a 0 estimation. We don't know how to estimate this probability. If we apply interpolation, we can get estimates in both cases, basically. In the first case, the interpolation gives a weight of 4 to this probability, to the probability for the trigram, so a higher weight, and a weight of 2 for the shorter context. And then you get probabilities that are very close to those of the trigrams, but not identical to them. So this is an effect of the weights that we chose. In the second row, in the second event sequence, we use basically only the bigrams, because we have only bigrams. So here we have 0. We just drop this part, and we get 0.4 and 0.6, which still allows us to estimate the next event in this sequence. So to summarize, using interpolated n-grams, it's possible to get sequences with a much higher feasibility, a much higher likelihood of being concretely executable against the application. The empirical results that we got were very good. Ku and I were really surprised by how good they were when we saw the numbers, because coverage increases dramatically. Transition coverage increases a lot. And with interpolation, you get an algorithm which is extremely stable in terms of what traces you give it to the input, the choice of n, a lot of factors. There's very little sensitivity, so it's a very robust algorithm which has very good results. And it was presented actually last week at ICSI in Hyderabad. OK, last problem I want to talk about, I'll try to be quick because I think I used most of my time, is the definition of the oracle, which is a key component of any test case. Here again, we have a lot of possibilities. The first one is, as usual, the most expensive. Do it manually. We can use the model as the oracle. We will see it's not always a very good idea. We have the crash oracle, and then I will talk a little bit about the possibility of automated oracles. So the manual oracle can be defined in terms of assertions that we add. So contracts, pre and post conditions, invariants, and expected test case results. Here you can see an example. For this application, I expect this invariant to hold. This either n is greater than 0 and total t is greater than 0, or they're both 0. This is just one example of manually specified invariant. Second possibility is using the model itself as an oracle. So if we run a given test case and we reach a given state, then this state must match the expected state in the model for such event sequence. So for add empty, in the suit we get a state where we have total 0, li 0. We can see if in the system under test we get a state that is equal to this one once abstracted. So this can be useful, but it typically expresses only a portion of the constraints that we want to enforce on the behaviors. So typically this is not enough powerful as a model. The crash oracle is always an option if by executing a given event sequence that is supposed to be a legal one, we get a runtime error, then we have probably discovered the bug. Again, this is very useful, but it will not expose more subtle faults where the functional behavior of the application does not produce an error, but still it deviates from the expected one. So an interesting option that has been proposed recently in the software engineering community is that of producing automated oracles by inference. These are not real oracles. Actually, for them, I prefer the term anomaly detectors because they are exposed to false alarms. So these are properties that are inferred from observations, that they are generalizations of observations. They can be used to classify new behaviors, new observations as accepted or rejected. If they are rejected, we say that an anomaly has been detected. This anomaly can be a real fault or it can be a false alarm, because I mean these oracles, these inferred properties, unless they are manually validated, are just approximations of the actual specifications of the system, which might reject behaviors that are perfectly legal for the application. If we look at the literature, there are 3 major families of anomaly detectors. One class is based on finite state automata, and one tool that implements them is KLFA. Second family is temporal invariant, and Synoptic is a tool that implements them. And the third family is data invariance, and Icon is an example of tool that implement them. Just to give you a quick idea of how they work, they take observations. KLFA needs only event sequences, and KLFA produces a finite state automaton that models the acceptable behaviors. If any new sequence is not accepted by this automaton, then it's regarded as an anomaly. In the second family, based on similar inputs, so observations of event sequences, Synoptic tries to infer temporal properties like always followed by, events that are always followed by another event, always preceded by, never followed by. If an event sequence violates any of these temporal invariants, it's regarded as an anomaly. So it's a potential fault. Icon infers data invariance. So for instance, after executing add, it's always true that items in cart this variable is greater than 0. So violation, again, of any of these invariants after a concrete execution is regarded as an anomaly. So what we did was to take 3 tools that are representative for these 3 approaches. In particular, we considered Icon, Synoptic, and KLFA. And we empirically try to answer these 3 research questions. How many false alarms do we get? Are these oracles eventually useful to detect real faults? And what's the cost for training and checking these oracles? So we use the number of subjects taken from the open source domain, and we measured the rate of false alarms as a function of the sample size. Of this sample size, 90% is used for training and 10% for cross-validation. So here you can see that for the icon, so for data invariance, the rate of false alarms is quite high. It goes down with a larger sample set, but still it tends to remain in the region of 0.3, so 30% of false alarms, which is quite high, and it seldom goes below that. For synoptic and temporal invariance, here it is slightly better for this application. Here it is worse. It's generally worse than for data invariance. For KLFA, it's definitely worse. We have a huge rate of false alarms, 90% of false alarms. So this was the first research question. The second one was about fault detection. So for the first one, RQ1, what can we conclude? The rate of false alarms is huge, whatever technology we take. So there's, let's say, a lot of research and work to be done there. Second research question, fault detection. So do these tools eventually detect real faults? So we took 7 real faults from the issue repository of Commons collection. And you can see that they are revealed. KLFA reveals all of them, but that's probably coupled with this. It also has the highest rate of false alarms. But in general, you can see that these anomaly detectors are good at revealing real faults. So they do their job. The problem is with too many false alarms. What about the cost, where the checking cost is typically very small, negligible? The training cost using a cluster, so using appropriate machines, number of machines, it can be reasonably low, the order of minutes. So to conclude on this part, automated oracles are an option, but more research is required because the false positive rate can be very high, even though real faults can be actually detected. Our rule of thumb that we reported in this paper is that if the cost for the definition of a manual oracle that can expose the fault is 30 times or even more than the cost of marking a false alarm as a false alarm, then anomaly detectors become competitive with manual oracles. If you don't have these, let's say, order of magnitudes of difference between the cost to check a false alarm and the cost to define manually an oracle, then anomaly detectors are not yet an option with the current state of the technology. So, my conclusions. So, getting a model, it's possible to get it through inference, but there's a number of issues about under and over approximation that have to be taken into account and must be optimized properly. Using a model is clearly doable. The key point is ensuring the feasibility of the test cases that one gets, because if test cases are not feasible, then this impacts transition coverage in the model, coverage of the code, and eventually fault detection capability. For what concerns the oracle, automated oracles are not yet there. This is our final conclusion because of this extremely high rate of false alarms. So I thank you for your attention, and I'm ready to take questions.